Hi there. This lesson is about sequences, and specifically arithmetic sequences. First, we need to start with some terminology and make sure we understand what we're talking about. A sequence is a list of numbers, themselves called terms, that have a pattern. There are finite and there are infinite sequences. Finite sequences have an end, like this set of numbers here, 1, 4, 7, and so on according to a pattern, ending with n. Or this one, 1, 4, 7, comma, dot, 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 meaning continue going. By the way, this bracket is called a set notation bracket, and it's used in math for a set of numbers. Terms are referenced by the symbol t or u commonly, although they can have other variables. These are the most common. These often have a subscript, and the subscript identifies what term number we're on. So using the example 1, 4, 7, 10, T1, which is also sometimes called A, is the value 1, right here. Subscript 1 representing the first. T subscript 2, or T2, is the number 4. T3 is the number 7. Again, 1, 4, 7 are the terms themselves. The subscript 1, 2, 3 are the term number. Sometimes those get confused. Make sure that's clear for you. By the way, if I'm going too quickly at any point in this presentation, just push the pause button and replay anything you need to. Alright, next, sequences are often described by formulas that relate to the term number. Here are a couple of examples. In this case, for t sub n and for u sub n, I'd like you to write the first three terms. Push pause, give it a try, and then check your work against mine. Alright, I have n equals 1, so I write t sub 1. I substitute 1 in for n wherever I see it. Term 1 then is 1/2. Term 2, 2 over 2 plus 1, or 2/3 is the second term. Term 3, substitute 3, and 3/4. So, this particular pattern is 1/2, comma, 2/3, comma, 3/4 in a set notation bracket. That's what this formula is telling us. Over here, u sub 1, 3 times 1 minus 2, or 1. U sub 2, 3 times 2 minus 2, or 4. And u sub 3, 3 times 3 minus 2, or 7. So this is the sequence 1, 4, 7 with the set notation bracket. That's how to work with the formulas. Alright, another notation to be aware of is called a sigma notation. Now with a sigma notation, this is a compact way of writing a sum of a sequence that uses a formula. Now it's important to distinguish this is for sums. Previously I was just using lists. The sigma notation has the sigma symbol right here. That means sum. It has a counter. Often it's the letter K, but it can be other letters like I or J or other things. It has a starting value of 1, and this number up here is the stopping number. And the whole thing taken together represents the sum. So, this particular sigma notation starts at 1, ends at 3, therefore has 3 terms. And the expression is k over k plus 1. So what we'll do is, we will substitute the lowest value of k, which is 1, into the formula. We'll write plus because sigma means add. We'll count by natural numbers and substitute the next number according to the pattern. And we'll keep going until we get to the stopping number, which in this case is 3. So we have 1/2 plus 2/3 plus 3/4. That's how sigma notation works. Now, you try this one. Try to expand it, push pause, and then check your work against mine. Alright, here we go. We substitute 1 in for I. That's my first term. I'm just putting a bracket there for visualization to help you see the separation of the terms. There's the second term with a 2 substitution, then I have a 3 substitution, a 4 substitution, and this particular sigma stops at 5, and since it started at 1, there are 5 terms. The simplified result then is 1 plus, 4 plus, 7 plus, 10 plus, 13. And you can see some of the same numbers according to a pattern we saw earlier up above, 1, 4, 7, and so on. We're going to come back to that pattern soon. A note about sigma notation and the number of terms. If the counter variable starts at some number k and ends at some number n, then there will be n minus k plus 1 number of terms. You can pause and think about that and consider why that would be. Try it out on this expression, I equals 2 to 10, and predict how many terms there are. You should have written 9 terms. Let's practice with sigma notation. Here are some patterns in these two examples, and what we want to do is recognize how the numbers are being formed. In this particular case, it looks like what I have is repeated multiplication by 1/2 on the number 3. So to write a sigma, I'll use the counter k. We do traditionally start at 1, although you don't have to. You could start at another number if that's your preference. This particular set of numbers has 5 values, so I'll go from 1 to 5. Starting number 3, I identified that I was multiplying by 1/2, and the counter goes in the exponent for the repeated multiplication. Now, if I try this out, putting 1 in here as substitution, I get the power 1/2 to the 1, which is 1/2. 1/2 times 3 is not 3. So I need to adjust this counter by subtracting 1. Check again. Substituting 1 in here gives the exponent 0. Remember your exponent laws, that a power with an exponent of 0 is the number 1. 1 times 3 gives 3, which is what we want. You could expand this and check to see that you get all those terms. Try the second one, and we notice a different pattern here. Now in this case, you can notice from 2 to 6 to 10 that what's happening, that's supposed to be a 2 there, what's happening here is I am increasing by 4 to form each additional number. Bit of a different pattern. This time, let's count from 1 up, and you'll notice I have another problem here. I'm missing some numbers, but I show the stopping number. What we need to do is try to figure out how many numbers are missing in here. They would be the numbers 14, 18, and 22. So taken together, it looks like I have 7 terms. So I'll count from 1 to 7 on my sigma notation, starting with 2, adding certain amount of the number 4. Now, I use the counter I, but if I start with 1, 1 times 4 added to 2 doesn't give me my first number. I need to offset this by 1. Again, adjust this and check. Put 1 in here. 1 minus 1 makes 0. 0 times 4, add 2, gives me my 2. This is the correct sigma notation. Let's move on, and I want to talk about arithmetic sequences. An arithmetic sequence is a sequence where each term differs by the same amount that's called a common difference, and it uses the symbol D to represent that difference. So the sequence we've seen a few times already, 1, 4, 7, 10, and so on, is arithmetic. I can find D by taking any term and subtracting the previous term, and I would see that it's 3. We can try it again with a different set of terms like 7 and 4, I'll get 3. Try it even with 10 minus 7, I'll get 3. What I did was choose any number, subtract the previous number, that's a difference, and it should be in common. So D is 3 is what I'm observing. Alright, term 1 is the number 1. There's some more patterning going on here we have to get at. Term 2 is that first number 1, and I add a common difference. I move to the number 4 by adding 3. Term 3 is the number 4, add 3, or, more importantly, it's the number 1, and I add 2 sets of 3. Term 4, well, that's 7 plus 3, or more importantly, another way to see it is 3 sets of the number 3. And all of this suggests a pattern, that any number, which is, by the way, called the general term, is based on the first number and a certain number of differences, and the number is always one less than what term I'm on. Let's check. On term 2, I need one difference. On term 3, I need two differences, and so on. Now, this is the formula for an arithmetic sequence. You don't have to memorize it, but you have to understand it and be able to use it. So let's look a little more at arithmetic sequences now. Here's an example, and I'd like you to determine, are these sequences arithmetic? Well, if they are, then any term subtract the previous term would be in common, like 2 minus 1 or 4 minus 2. Since 1 doesn't equal 2, this is not arithmetic. Try the second and third one, push pause, and then check your work. Alright, this one, 5 halves minus 1 half, is 4 halves, or 2. 7 halves minus 5 halves, well, that's 2 halves, or 1. Again, not arithmetic. The next one, 7 subtract 12 is negative 5. 2 subtract 7 is negative 5. Negative 3 subtract 2 is negative 5. This one is, and the common difference is negative. What that means is I am increasing by a negative amount, or I am decreasing. It's still a common difference. One last example. I'm telling you in this case that these are arithmetic sequences, and based on the information, I'd like you to identify the first 5 terms. You may want to pause and give it a bit of thought and see what you can come up with, and then push play again. Okay, assuming you've given it a little bit of thought, let's have a look here. The common difference is any number subtract the previous number, so negative 6. Again, 5 minus 11 is also negative 6. That's my common difference. Now, I have my first term, it's 17. Let's use that formula. The fourth term is based on the first term and 4 minus 1 common differences. So 17 and 3 times negative 6, which is 17 minus 18, or negative 1. That's my fourth term. My fifth term is the first term and n minus 1 differences. First term being 17, n being 5 minus 1, so 4 sets of negative 6. And that's going to be 17 plus 4 times negative 6, 17 minus 24, or the number negative 7. Having a look at the next example quickly. Now, little trick here, I didn't give you the first term. Gave you the second term, and a common difference of 3, meaning I'm decreasing by 3. You could count backwards and say 12 and 3 makes 15, and that would be true, but let's try something a little more sophisticated using the formula for practice. Alright, there's my formula. In this case, I'm going to use the second term for the nth term. The first term is something I don't know. I know that I'm on term 2 when I'm using 12, and I was told my common difference is negative 3. So I have 12 equals a plus 1 times negative 3, or a equals 12 and 3, 15. There's my first term. Alright, you can figure out why this would be, but the third, fourth, and fifth terms, I'll just provide them to you so that you're sure that you know them. They are 9, 6, and 3. There you go. Good luck with this lesson.